the
It's like,
screen.
how's party girl?
Oh, dear Lord.
Party girl.
What do you do?
Oh.
Yeah. Yeah, Janine,
This concludes our weather-related focus trip. Thank you for your cooperation.
Yay.
We survived it.
we're all safe, okay. No, Janine, she's in the other half of the class. And, well, I was just kind of bantering back and forth, and I said, why are you all taking this class? And Janine goes, I'm here for the party. Yeah, nice, okay.
Very nice.
Here we go.
Is
At
it?
least she was honest. Got to give her credit for that. We're just here
Oh,
for the
this is
party.
okay.
Did you give Alan a mask?
Huh?
Yeah, he's had it
that's
since
He
been
needs
happening.
one.
I never noticed him.
Vector needs a
That's
mask
just
too,
like
I think that would really.
Yeah,
look
Vector
good.
needs a mask.
Oh,
Someone needs
Just
to
a
like make a
little
little
one.
sticker or something.
That is a good, yeah, I like that. Okay, so, all right, so let's talk about the Moving Man Lab, okay? And so here's, and I also sent you all the notes, so have you started that?
Yeah.
Okay, good. Okay, so here's some big ideas that you have to get. We're going to study some pretty complex motion, but you can break them down into some pretty simple ideas, okay? And those are those golden rules that I sent out on the lecture notes. So golden rule number 1 is that if you change direction, your velocity has to change sign. Now, let's not get technical and go, well, what if you're moving around in a circle? That is not part of the story right now. So imagine that you are you're like the dude in the program, okay? You could only move back and forth in one dimension, okay? You're like Flat Stanley. You're stuck in one dimension. That's all you can do. So if I'm going like, let's say for example, I'll use ow as like my pointer so I know here's the direction of my velocity vector, right? So this is pointing in this way. If I stop and then come back, okay, that velocity vector is going to change direction. So if I'm going this way, ow is pointing this way. If I'm going that way, ow is pointing that direction. No exceptions whatsoever. If you change direction, your velocity has to change sign. Now, here's the other thing I want to get out of your minds right now. That positive velocity means that you're going in a particular direction, okay? It doesn't. Positive velocity just means that you're moving in whichever direction that is defined. Typically, your book will define positive velocity as being right and positive velocity going up. Negative velocity going left, negative velocity going down. And we'll use that most of the time. But notice that isn't one of the golden rules. So, if you've got a situation where you're moving, and there's a couple of different ways that you can represent motion. It kind of depends upon what you want to do. And I'll show you some different ways. So let's say that you've got the dude, okay, and he's going to walk in this direction. So every motion that you're going to study in this class is only going to fall into one of two categories, okay, and there are only two categories. You're either at a constant velocity, meaning that the velocity vector is pointing in the same direction and that magnitude is staying the same, or you're accelerating, which means the velocity vector is getting bigger, the velocity vector is getting smaller, or the velocity vector is changing directions. Literally, every problem you work is only going to be in one of two things. It's either constant velocity or it's accelerated motion. There is nothing in between, okay? It's a binary function. Either you're at a constant velocity or you're accelerating. So let's start with the constant velocity one. So one of the things that you want to do is you want to define a reference point, okay? So here's the classic example. So I said, Ryan, describe your position inside the room. What would you say? If I said, Dr. Boss is going to walk in this room, he wants to find you. How would you describe your position?
Middle of the room, like the middle desk. On the
Now you have to define it from a point.
from a point.
You can pick any point of the room to describe where you're at.
Any point in the room. This is hard, put me on the spot.
Literally, yeah. Called the reference point, in this case, the reference spot. Pick the door. He walks in that door.
Uh-huh.
You can define it in terms of steps. Take so many steps in a particular direction.
Probably like a good 6 steps,
Which way?
straight from the door.
Straight from the door, then what?
Then turn left, about good 3 steps.
Okay.
Right there.
So what Ryan is going to tell Dr. Botts to do is that he's defining his position relative to the door. He picked the door as the reference point. He's going to say from that reference point, you take 6 steps north, straight, however you want to define it, 90 degrees, I don't care. Then you're going to turn, and then you're going to take 3 steps this way. So if he comes through that door, he's using that as the reference point. Now, you could also define that in terms of distance. He could say, hey, I am 6 meters away from the door north, and I am 3 meters away to the west. Okay, so we could go north and west. We could also do that. Now, he says, ooh, Mr. Burkamp, I really like the big water jug in the side of the room. Hey, I'm going to define my position that way. He could say, hey, I am 8 meters to the east of the water jug. Find the water jug, I'm 8 meters over here. Both descriptions about where he is equally valid. Okay, they are both equally valid. It's just where you start. Now, the same thing is true. Like if I take this rubber stopper and I throw it up in the air. If I make my hand the reference point, you would say, oh, it goes away from my hand and then it comes back to the reference point. If I make the ceiling the reference point, you would say it goes towards the reference point and then it comes back away from the reference point. The motion is the same. It's just how you describe it. Okay? So typically, your reference point is where you begin, but it doesn't have to be that way. Okay? But that's typically how this deal plays out. So, if we're going to make the reference point 0 meters, so on the position time graph, if we define these positions as being positive numbers, 1 meters, 2 meters, 3 meters, whatever that is. So on a position time graph, every position time graph can only do one of 2 things. It can either curve or it can be a straight line. That's it. There is nothing in between. So if this is my position time graph, and I draw a straight sloping line like this is where this turns into a logic problem. This is a position time graph. This is meters. This is seconds. So this slope is going to be meters over seconds. So the slope of this line is going to be velocity. So if I have a straight sloping line on any position time graph, that means that I have constant velocity because the slope is the same. So anytime you have a straight sloping line on a position time graph, that's constant velocity. Now, if something's at rest, and at my age, I hate to use this term, but it's like a flat line, okay? So I hate that term. Especially during first and third block, I had to go run out and run through 10 meters out in the hallway. That was boring. I died. Okay, so a flat line on a position time graph just means that you're at rest. Because again, what's the slope of a horizontal line?
0.
0. You're at rest. Your position isn't changing. Now, if at this point one of 3 things can happen, or one of 2 things. We could go up, we could go down. So if this starts to come back down like this, that means I'm returning back to that reference point, and it's changed direction because I went from having positive velocity to having negative velocity. I changed direction. If I keep going up like this, that just means that I'm still going in the same direction. So if I define me as the reference point, if I do this, I'm going away from the reference point, I stop, and then I keep going away from it. If I do this, I go away from the reference point, I stop, and then I come back towards it. Okay? So if you see something change direction, you know your velocity has to change sign. There's no exceptions to that rule, none whatsoever. So the other thing that can happen on a position time graph is that you could have, and this is what I call the Mick Jagger lip curve. Okay, so if you know anything about Mick Jagger, he's got these huge lips. Oh my God, I'm Mick Jagger. I'm talking and I've got huge lips. Okay, so this is what we call the Mick Jagger lip curve. Okay, so you have the top of the lip, the middle of the lip, and the bottom of the lip. So if this is a position time graph, if you had the top of the lip, Josh is not your sister, you, okay? So you have all your sister under the bus on this. So if you've got the top curve of the Mick Jagger lips, is that object slowing down or speeding up?
Slowing down
How do you know?
because the slope is lessening.
Yeah, beautiful. The slope is becoming more shallow, right? I'm approaching 0 meters per second. So the top curve means that I'm slowing down because the slope is becoming more shallow. The bottom curve would be doing what?
Accelerating.
Accelerating.
You'd be accelerating and you would be speeding up, okay? Middle of the lip would be
Constant velocity.
So every time you look at a position time graph, these are basically the only three things that can happen. You have a curved line that's showing it speed up, slow down. You have a straight sloping line, which means you're at a constant velocity, or you're speeding something up. Okay, that's it. Those are the only three things that you can do on a position time graph. Now, if I take this, and let's say that I break this over like this, okay? Anytime, and for those of you that are math nerds, you have a relative maximum in this case on a graph. So this means that you're going to change direction. Okay? So because you went from a positive slope to a negative slope. There you go. Now, when you have a curved line like this, and you want to find the velocity at some point in time, I'm never going to ask you to do this, but you need to know the concept. Because a lot of times what we'll talk about is what's called instantaneous velocity. How fast are you going at a particular point in time? Now, technically on a position time graph, when you have a curved line, yes, well, the calculus is you take the derivative of it. But the old school way to do it is this, you draw a tangent line.
Yep, tangent.
So a tangent to the curve at any particular point will give you that instantaneous velocity. Now, if it's a straight sloping line here, you can't draw a tangent line if you tried.
Yeah.
There's no tangent, there's no curve to it. Because you don't need to, because the slope is the velocity at any point on here. So if you want to find an instantaneous velocity when you're accelerating, and that acceleration, and here's the other thing I want you to get out of your minds right now. When I talk about acceleration, I don't always mean speeding up. It might be slowing down, it might be changing direction. So get out of your minds right now that acceleration just means speeding up. All it means is that I'm changing that velocity vector. Bigger, smaller, changing the direction of it. Now, an interesting thing happens up here. Up here at the top, if you were to draw that tangent line, hold on, why didn't that? When I draw that tangent line up at that relative maximum, that means that instantaneous velocity is going to go to 0. So, and this is on the lecture notes, when something changes direction, it has to do 3 things. It's got to slow down, because that line's going to become more shallow. You have to stop when you're going to have a tangent line that's horizontal. And then you're going to speed back up. So if I take this rubber stopper and throw that thing up in the air, that's the classic example of doing those 3 things. So on the way up, it's slowing down. It hits the maximum top. That's when it stops. And then it speeds back up on the way down. Okay? So you're going from starting at high velocity, slowing down, stopping, and then speeding back up. Okay. Now, on a velocity time graph, here's the most common misconception that happens on a velocity time graph. Let's do this. Okay? So, meters per second, there's second. So let's start with the basics. The slope on a velocity time graph gives you what?
Meters per second.
Meters per second squared, otherwise known as
Acceleration.
acceleration. Because you got meters per second divided by second. That is one of the things you just have to know cold. You can either memorize it or you can just look at the units and see that it works out, okay? It doesn't make any difference. So, on a velocity time graph, again, it can only show one of three things. It can either show you speeding up, it can show you moving at a constant velocity, or it can show you slowing down. That's it. Now, here's what you're tempted to look, and here's 0 meters per second. You're going to see that, and you're tempted to go, oh, you're starting at the reference point. So that doesn't have anything to do with the reference point. All I know is that I'm at rest. So if this 1 kilogram mass is the reference point, okay, and I'm defining this direction as being positive. So I could be over here and then start moving with a positive velocity, okay? I could start at the reference point and start moving with a positive velocity. I could start over here and start moving with a positive velocity. So when you look at a velocity time graph and it starts at 0, that does not mean you're at the reference point. All you know is that you're starting from rest. That's all you know. And then you're defining this direction as being positive. So here you've got positive velocity, positive acceleration. Anytime, and this is without fail, there is no exceptions whatsoever. Anytime your acceleration and velocity have the same sign, you're speeding up. Okay? No exceptions whatsoever. None. So that's what's happening here. I'm starting at 0 meters per second, and you can't go any slower than 0. Even freshmen cannot go slower than 0 meters per second. Okay? That's it. They've tried. I've seen them. So if you're at 0, the only thing that you can do is go away from 0 meters per second. So if you're trying to figure out if something is speeding up or slowing down, I'm going to give you 2 methods. I don't care which one you pick, just understand it. So if you're trying to figure out if something is speeding up or slowing down, if you like signs, like I'm looking for a sign, good. If you're looking for a sign, look at the sign of your acceleration and velocity. If your acceleration and velocity have the same sign, you're speeding up. So then when I get to this point over here, I still have positive velocity, but now I have a negative sloping line. So that means that I would have negative acceleration and I'm slowing down. So here I've got positive velocity, negative acceleration, I'm slowing down. But look what happens. Here's 0 meters per second. So this is the other way that you can view this. On this segment, I'm going away from 0 meters per second, which means that I'm speeding up. Okay? This one, I'm approaching 0 meters per second, which means I am slowing down. So if you just want to look at this line in terms of where it is relative to 0 meters per second, that's cool. Okay? If you like signs, look at signs. But here's what's important. When this crosses 0 meters per second, what have I begun to do? I've got a negative velocity, but I still have a negative acceleration, which means that now I am
Speeding up.
speeding up. Okay? So now if I've got negative acceleration and negative velocity, now I'm speeding up. So I'm slowing down, and this is what I said. If you're going to change direction, you have to do 3 things. Slow down, stop, and speed back up. That's what's happening here. I'm slowing down, I'm stopping, I'm speeding back up. Okay? Now, on a velocity time graph, and I've gone through these in the notes. If you can find this area between 0 meters per second and this line, that gives you the displacement. So that's what y'all are going to do on the lab tomorrow. Okay? You're going to collect some data and you're going to try and find it. Now, it's weird. I've got actually have back-to-back labs. So tomorrow you guys are going to be at home and you're going to trust the other group to get the data that they're going to give to you. On Monday, you all are going to do a separate lab, and they're going to trust you to get them their data. Okay? That's kind of how I see it playing out. What I might do, this is what sucks about alternating days. Or I might have just like a lab day where you all just get all the data, and then you take basically another day to crunch the numbers. And then I might do that with the other group. I'll sort that out. But anyway, we've got two labs that we have to do back to back. So riddle me this. Would you all just rather have like one big lab day where you get all the data, and basically I give you the other day to crunch all the numbers? Or would you rather have like you guys do the lab like tomorrow? Would you guys trust them to do the lab, or do you guys want to wait until Monday and then do both labs in the same day?
Both labs in the session.
Yeah, I kind of think.
You'd rather do both labs in the same day as far as collecting the data?
Yes.
Okay. That's going to be tough. Okay. Okay. That might work out well, because then I've got to think through the logistics of that. I will try to make that happen, but I don't make any guarantees, but I'll try. Okay. This is weird that it's unusual that you have back-to-back labs, but that's just how it's going to play out. Okay, so anyway, so the lab that you're either going to do tomorrow or you're going to do Monday, but here's the lab that you're going to do. You're going to calculate how far this card is going to go, and it's going to hit the wall, and it's going to bounce back. And you're going to draw a velocity time graph. But on any velocity time graph, the area here or the area down below is the displacement. Now listen to me, that's important. It's the displacement, not the distance. So when you look at displacement, and I want to write one formula up here that you have to get straight. So displacement, and this is going to be important, is P minus P0. This is going to be position final minus position initial. So let's say, and here's a simple idea. So let's say that here's Al, and here's the reference point. Okay? So if Al starts here, and he walks, and we define these as being positive positions. So Al starts at 0, and he ends up 5 meters away. So on a position time graph, Al would start here, and he would end up here at 5 meters. So one way to calculate displacement on a position time graph is just basically find your change in your y-axis. 5 minus 0, hey, here's my final position, here's my initial position. If you were to use this formula, okay, it's position final minus position initial, it'd be 5 meters minus 0. That part's the simple one. Where you run into trouble is that if he turns around and he goes backwards, okay? If he starts at 5 meters and ends up back at 0, then it's going to be 0 minus 5, and then his displacement will be negative 5 meters. So if he turns around and he comes back, as indicated on this position time graph, because of the fact that it's changed slope, now he has changed direction. Now, from here to here, he has a positive displacement of 5 meters. From here to here, he has a negative displacement of 5 meters. So that leads us into the two big terminologies that you need to know. And this is actually why that sign is relevant up there. You have two primary quantities that you're going to deal with in physics. Scalar quantities and vector quantities. So, scalar quantities only have magnitude. What that means is that it's just a number. There's no direction associated with it. So it's like, what's the mass of this gray thing in my hand? Oh, that's 1 kilogram. So mass is an example of a scalar quantity. It's just a number. Speed is a scalar quantity. Okay? So if I ask you, hey, how fast are you going? You're going to look at your speedometer. Okay? your speedometer in your car only tells you how fast you're going. Okay, it doesn't tell you which direction. It only tells you how fast you're going. You'll see that energy is another one. Okay, that's a scalar quantity. I have a certain amount of energy, but it isn't directed in any specific direction. Now, if something's a vector quantity, which is up here on the board, okay? So a vector quantity has two things. It has magnitude, but it also has direction, okay? Now, if I say, hey, Ryan, how fast do you go when you get to school? He goes, oh, probably about 40 miles an hour. So all he's telling me is speed, okay? Give him the benefit of the doubt. Okay, he's just telling me speed. That's all I know is that he's going 40 miles per hour. Now, if I said, Ryan, what's your velocity? If he says, oh, Mr. Burkamp, I drive 40 miles per hour north. Now, as soon as he tells me he's going north, then it becomes a vector quantity. Because now, not only do I know how fast he's going, now I know which direction he's headed, which means he has to live south of school. Okay? So now I know where not only do I know how fast he's driving, I know which direction that he's driving. So, in terms of vector quantities, displacement is a very common one. Velocity, acceleration, force. Okay? We're going to get into some other ones later on, but these are the ones that are going to be most commonly used. So, displacement, velocity, acceleration, and force. So, if something is a vector quantity, we need two bits of information. We need the magnitude, how fast he's going, and then we need the direction. So, if your car not only tells you how fast you're going, but it also has like a compass, that's actually like, you don't have a speedometer. It sounds like something out of Jurassic Park. You actually have a velocimeter, because not only is it telling you how fast you're going, it's telling you which direction that you're going. Okay? So if you're like the physics nerd, you go to the car dealership, you need a speedometer? No, I want the velocimeter. Oh, cool. Nerd. Okay. And I want my speedometer to show in meters per second, not miles per hour. Thank you very much. Okay, that's really hardcore.
That would not
Huh?
that would not end well for me.
Why?
Because I'd have to you'd have to convert it while you're driving, and I'd definitely be speeding 24/7. I had that, like, there's no way I would put in the effort to go.
Okay, just like, I'm just going to go fast.
I'm just gonna.
Fast.
You just
Yeah.
gotta like stick with the flow of traffic.
Or you can do that, unless everybody else is going to do
Yeah, I
that.
don't look at the speedometer.
I just immediately set my cruise control 5 over.
Okay, there you go.
Well, you can't get a moving violation for it, so
Okay,
why not?
all right, there you go. Simple as that. Okay, so what we're going to do is we're going to look at kind of some simple examples of how this plays out. So if I take this rubber stopper and throw it up in the air, does it accelerate?
Yes.
Yes.
Yes. So if something accelerates, guess what else you have to have to cause that acceleration? A force. Because Mother Nature is a lazy prima donna. And Mother Nature isn't going to make velocity vectors change unless you make them. So the other way that you can represent this thing being thrown up in the air, okay, there's a couple of different ways that you can draw this. One is, and this is what we're going to use a lot, we're going to use velocity vectors. So I don't know what the velocity vector is. I don't care what the velocity is. All I know is that it's some relative amount of velocity. Okay, that's all. Now, so this is when I let go of it. Okay, so that's the velocity it has at the very instant that it leaves my hand. So here's my hand, okay? And here's that rubber stopper just right after it leaves my hand. Now, when it leaves my hand, one of three things can happen. One of three things. Either that velocity vector is going to get bigger, which means it's going to speed up as it goes up, which would be cool. Okay? Yeah. It's going to stay the exact same, which means that whatever velocity I have, that I give it is the same velocity vector it's going to have as it goes up. So that would be a situation where you have no gravity whatsoever. So if I could shut off, this would be the ultimate thing to have in a physics classroom. If I could have like a big gravity switch, say, okay, this is going to be like the no gravity zone. And I could throw that thing up in the air. As soon as I let go of it, it would maintain that velocity and just keep going up. That's actually what Mother Nature prefers. Because if you look at Newton's first law of motion, and we'll spend a lot more time talking about this, Newton's first law of motion basically says Mother Nature is chilled out. So if you give it a velocity vector, it wants to keep that velocity vector. But if it's at rest, it wants to remain at rest. So if you see a velocity vector changing, that isn't what Mother Nature wants. Mother Nature wants that velocity vector to stay the same. So it could get bigger, it could stay the same. In this case, what's it going to do though?
It's going to change.
It's going to become smaller, right? So then we could go, oh, here's V2, right? And there's like V3. So this is showing my velocity vectors getting smaller. Now, anytime your velocity vectors change, that is an indication that you're accelerating, okay? Now, so my acceleration vectors, because acceleration is a vector quantity, just like velocity is a vector quantity. So this is showing me two things. It's showing me the magnitude, okay, because it's a vector quantity, how fast I'm going, and which direction that I'm going. So this satisfies the definition of it being a vector quantity. So one of two things is going to happen with my acceleration vector. My acceleration vector is either going to point in the same direction, or my acceleration vector is going to point in the opposite direction. So what do you think is going to happen? Lauren? When I draw my acceleration vector, do you think it's going to point in the same direction, it's going to have the same sign, or do you think it's going to point in the opposite direction and have a negative sign?
Opposite,
Why?
because it's going to be coming back down.
It's true. But no. So, yes?
Because the acceleration force acting on it is making it slow down, so it's an opposite force to where it's going.
Okay? Now think about this. On the way up, what's it doing? Speeding up or slowing down?
Slowing down.
Slowing down. What's one of the golden rules? If something slows down, what do you know about velocity and acceleration?
It's going to hit 0.
No. That isn't one of the... They have to have the
Different sign.
opposite signs, right?
Opposite signs, yeah.
So if I have positive velocity, that means on the way up, I'm going to have negative acceleration. Okay? So anytime your acceleration vectors point in the opposite direction of your velocity vectors, that means that you're slowing down. Now, on the way down, what's going to happen to my velocity vectors?
Speed up.
It's going to speed
They're going to get
bigger.
bigger and they're going to point
Down.
down. So on the way down, I would draw those like, let's change up the color, get a little radical.